Well, it's great to be here, and this is a follow-on from some of the things we talked about in Forno and some of the things we talked about in Malaga. So it's kind of part of an ongoing journey. Just to let you know a little bit about our facility, we have both a capability in Manchester and a capability using synchrotrons. The work I'm going to show today is primarily at ESRF, but we also have a team of about 30 people at Diamond, and Chris is one of those people. This year we were lucky enough to go and visit the Queen to get a prize. So, my mum was very disappointed to hear I'm now an engineer, but she was pleased to hear that I got to see the Queen. So you win some, you lose some. We're just moving labs too. So we have a very big lab, and we have a total of 10 X-ray scanners, and we're just filling this lab at the moment with our equipment. So we're in a stage of transition. And we do a whole range of imaging work, from materials through to art and electronics. And we do work with a great range of people, some of them are in the audience today, both in Manchester, both across the world and in the UK. So the idea really of the work we're doing on crack tips is to understand the relationship between crack growth and crack morphology and stress fields in crack. So today I'm going to focus on the stress work because I think that probably is a sort of a unique aspect of some of the things we do, and James and others have talked about it, and Pablo have talked about the imaging work. So what we're looking at is this overload problem, 70% overload. We're looking at this, what happens to the crack tip as we go through a 70% overload. Coming back to some of the questions we asked last night, so entertainingly about closure, residual stresses, the effect of K, is K effective important? These are all important things, and I'm not going to answer those questions, but I may just add a few more ideas into the mix, and I would be really interested to have this discussed perhaps tomorrow when we've had some more wine and we're ready for discussion. The material is a magnetic steel. The yield stress is 600. We've tested it. This experiment I'm going to explain is in plane stress. We've also done experiments in plane strain, but I haven't got enough time to go through the whole data set. As I said, the key points really are we're cycling at 35 MPa. We go one cycle before overload, so we've done many cycles, but we go through one cycle before overload. We then go through an overload, and then we look at a number of positions after overload. So the crack is roughly the same location. We do 40 cycles, 2,000 cycles, 8,000 cycles, and 37,000 cycles. And by 37,000 cycles, we've grown 2 millimeters past the overload location. The geometry is very simple. It's a CT sample, and by measuring with 2 detectors, we can measure the strains in the 2 in-plane directions. We can measure strain in the XX and the YY direction. And in addition, we superimpose upon that, so that measures elastic strain, and by doing DIC, as you've already familiar, we can measure total strain. So we have total strain by DIC at the surface, and we have elastic strain in the bulk. A 3 millimeter sample, a 3 millimeter thick sample. This is the setup, so there's the camera on the beam line, and there's a little CT sample hanging here. You can see the area we're monitoring, and the X-ray beam is coming straight towards us in this orientation. I think it's coming straight towards us from the way we're looking. So the results, we can get really detailed pictures. We're using a gauge volume that is around, if I forget what it was in this, it's 60 microns, I think. So we're using a gauge volume of 60 microns. So we make thousands of measurements around the crack tip, and you can see this is the K max field. You can see the field around the crack tip, and we can measure the strains. The elastic strains go up to about, well, this sort of region. Okay. And we can measure the strain in the other direction, in the crack growth direction. So we can map. We have a wonderful tool to measure strain, and I'm not going to show all the results. I'm just going to show you some maps and then some line scans. And on top of that, we measure with DIC the plastic strains. And of course, the plastic strains are much larger, 5% in this case. I think that's in percent. I think it is in percent. Is it in percent? As Pablo will remember. Is that in percent? Where's Pablo? Yeah, I think it's in percent. Must be percent. Okay. Yes, it is in percent. So you can see we can compare elastic strains and total strains. Our DIC measurements were not ideal. We're learning that we probably need two detectors, two cameras to get really good measurements when you're doing DIC. But when you're travelling across the country to do these experiments, sometimes you travel too light. We know now, we'll now do better experiments. I'm going to show you a little series of images. I apologise that the strain values and the stress values will change. So these are the stresses. So we've taken the strains in plane and we've used the plane strain condition, plane stress condition to work out the stresses. So these are in stress. And what you can see obviously is a very large stress field ahead of the crack at K max, and you can see a stress field at K min. The axes have changed, but you can see a compressive field here, and we've done our very best to know where the crack is. It's easy to find the crack at K max. The crack tip is here, but it's harder to find it in K min. But I think, having looked at this long and hard now, there is kind of evidence. I wasn't sure originally, but I think we have some evidence of some compression, some slight compression. When you increase the load to overload, you get the same kind of profile, but obviously the plastic zone increases. The plastic zone is about 3 millimeters, comes out to about here, so you can see the stress field. And when you unload, not surprisingly, you get a much bigger compression behind the crack. Well, not behind the crack, actually in where the crack tip is. You can see this is actually where the crack tip was. Not surprisingly, nothing really very surprising. But then as you continue to grow the crack, what you can see is the peak stress starts to fall. You still get this large compression, which is the result of the overload. So the crack has to grow through that large overload, and the stresses at the peak is smaller than you would otherwise get. I'll show this on line graphs in a moment. But the other thing to notice is you get this tensile peak here, just about 2 millimeters behind the crack. And that's something I would like your input on. So we'll look at that again in a minute. As you go on 6,000 cycles, again, you've still got this compression zone, and the tensile peak is lower than it was before overload. I'll show all this in a much easier line diagrams in a minute. But the key point here is when the crack has grown. Now this is where the crack is now after 30,000 cycles. The crack is here, but you can see this compression. 2 to 3 millimeters behind the crack, and you can see the compression here immediately behind the crack. So you can clearly see that the crack faces are touching behind the crack, near the overload position. And we use crack opening displacements to measure the crack opening displacement, and this shows the opening displacements across the scheme. So the blue curve is the original case. We can see an opening. This is where the crack is, or it thinks it is. You can see if you go to overload, obviously that goes higher. And then after overload, you come back. As you grow through the residual stress field, you get these lower openings. And then by the time you get to the 37,000 cycles, you're pretty much back to the same crack opening displacement behind the crack as you were in the original baseline fatigue case. If you look at all that data I took, and you look at the ligament, and you just look at the distance from the current crack tip position, what you see is traditionally the traditional blue, that is just before overload. You can see after overload you get this green curve, you get this hump here, which is retained when you then continue to load. But you can see that the peak load drops significantly after overload, because of the residual stress field. At least that's my conjecture. So this is now much lower, and that grows through 40, 2,000, 8,000, and by the time you get to 37,000, you've gone back more or less to the same crack tip stress field that you had at the beginning. So that's K max. Now look at K min, and what you see is originally a compression here. And this is the original curve, and what you can see is after the overload, which is after overload is the green curve, you can see a massive increase in the compressive stress in the region of the crack tip, And as I said, you see this tensile hump here. So you get a tensile hump here, which is arisen from the overload. And I'm not quite sure why we get this tensile hump at 2 to 3 millimeters ahead of the crack. But you can see as the crack grows, the minimum increases slightly as it grows through the residual stress. And by the time you've grown out of the residual stress, you get a crack tip stress field that is really quite similar to the one you had in the first place. Okay. Oops, there's one missing there. Where's that gone? I thought I had another image. I'll just see if I can find that. I think I've lost an image. I'm sorry. Maybe I left it out. Maybe I left one image out. I left one image out. I'm sorry. One image that is really helpful, which I have left out, and I apologise. I don't think it's crept in somewhere else. Is that if you compare the difference between K-min and K-max, what you find is the overload condition, the 40, the 2000, the 8000, and the 37 are identical. In other words, the strain excursion from K-max to K-min is exactly the same for all of those runs. So each one of them has exactly the same peak. The reason this is lower is simply because it's starting from a compressive field and is moving to the tensile field. So that residual stress field ahead of the crack is causing a decrease in Kmax. I'm sorry, I've left that image out. I can show it tomorrow if there's interest. We also fitted it to the data, fitted the data to models, and you can get out the K effective. And actually the K effective is about 21% lower than the K we applied before overload. It's about 21% lower at K max. And then as we go through 42,000, you can see there's just a slight increase in the K max as it rises, in the delta K inferred, and it rises back towards the value it had just before overload. So we get a decrease in the K effective as you would determine it over that period of cycles. Okay. So just to summarise, diffraction shows a large plastic zone about 3 millimeters ahead of the black crack, as you expect. You get an overload. That overload causes Kmax to fall because of the large compressive plastic zone at Kmin. This gradually recovers as the crack grows through the residual stress field, and by the time it's grown about 2 millimeters, it's back to a value similar to the value it had before overload. And we see crack face closure at the point of the overload when the crack is 2 millimeters ahead of the crack tip. Okay, that's all.
Thank you.